the distance. The distance is the real challenge. How do you determine the distances to objects when they're in space? And so for this, we have the cosmic distance ladder. This is super clever. First time I learned this, just brain explode. And so there's quite a few different techniques here. And they all lead to this Hubble constant that characterizes the expansion of the universe. But maybe let's break it down instead of these very technical terms. Let's break it down to the conceptual stuff. Conceptual? Sure.
Conceptual.
So the cosmic distance ladder, also known as the extragalactic distance scale, is the succession of methods by which astronomers determine distances to celestial objects, stuff in the sky. A direct distance measurement of an astronomical object is possible only for those objects that are close enough, within about 1,000 parsecs to the Earth. And so that's say, like the sun. The sun we can see the distance of, it's just right there. If things are close to the Earth, 1,000 parsecs, not too far, then we can use parallax. Parallax. So parallax is this. So say if it's in July and we look up toward like this, so here's the sun, here's the Earth, and if it's this part of the year, this is July, this will be January. And so if we look up at this angle, we see the star in question and then the background stars. And so that looks like this. We get the star in question and then the background stars. If we wait for half a year and we come around this orbit, we look up at that same star, we'll see the background stars change. And based on, and we know the angle, how's it? We know the angle, and then therefore we can get the distance.
Well, we know, what do we know? That we're the distance from the sun to the Earth.
To the Earth, that's 1 AU.
At summer and, well, in your case, in July and January. And then we can know the angle shift as we go from July to January. And then there's some trigonometry involved. We can get the distance to the star. Because what is it? Angle, distance, side, angle.
Side, angle. One of those. Yeah,
side, angle,
I learned this in geometry. Yeah. Yeah, cool. So we can figure out the distance from our sun or from Earth out to these stars if they're close. Now, the further away they are, the smaller that angle becomes is very difficult to resolve. You have to switch to a different method. But for stars that are close, sure, it'll work.
So what do they use for? I think it's like the next step in the ladder is we find variable stars, ones that like pulse at their brightness pulses at specific frequencies, and we can use the parallax to get the distance to a specific variable star, so we know what the variation looks like in its period, meaning how often does it vary its brightness. So we know the distance, so we know what the brightness of that particular star is, and then we can go beyond parallax and look for those variable stars and get the distance that way. And that would be like rung 2 in the ladder.
Yeah, exactly. Do you know rung 3?
I think rung 3 is a supernova, right?
Okay.
Something.
Cool. That's the one I'm familiar with. I didn't know if it was rung 3 or not.
I don't know. I mean, I think it's more complicated than this, but because that picture we saw with all the different connections, I think it's complicated.
I mean, actually, if this picture is correct, you just about got it.
Oh.
So there's parallax limits. So that's just geometry. And then you go to parallax as Cepheid variables in the Milky Way. And then that gets you a new parallax limit. And then beyond that, we switch to galaxies that have Cepheid variables and type 1 supernovae. So it's like, if we know how far these stars are just by direct measurement, then we can match these to stars that have this variable property. Then there's like an overlap in the rung and the ladders. And then we go to galaxies that have the previous step and then also this new step, and then we can match that up. And so it's like this it's not leapfrog. It's you take one step forward with your right foot, and then your left foot matches it. Then your right foot forward, then your left foot matches it. And so your right foot's always reaching out into something that you have to figure out with physics. And if you can use your left foot for the old method, then you can say, okay, I know how to match this up. I can keep going forward, this ladder. Okay, so we're now up to type 1 supernovae. So type 1 supernovae is I guess it's a specific type of supernovae. It's when they are small stars that don't explode. They explode, but they leave a little core, as opposed to type 2 supernovae, which are just big stars, just explode, they're gone. So when the small stars explode, they let out their outer shells and leave a little core. If that core is able to steal gas from another star, then they reach the Chandrasekhar limit. Chandrasekhar limit. The Chandrasekhar limit is the maximum mass of a stable white dwarf star. The currently accepted value of the Chandrasekhar limit is about 1.4 times the mass of our sun. So the white dwarf star, the inside of a dead star, a small star, if it can steal enough gas from a neighboring star, then when it gets to 1.4 times the mass of our star, it has enough gravitational force to collapse in supernova. And so if that always happens at the same amount of mass, that means we can map out the distance. So if it's so bright and if it's at some distance and it's this bright, then we can figure out the distance. If it's further away and it's dimmer, well, if it always supernovas at this 1.4 times the mass of our sun, then we know how much light it generates. If it's dimmer, it must only be because of its distance. Similar to how a candle close to your eye is very bright, but that same candle making the same amount of energy, making that same amount of light, when it's across the room, is just dimmer. It's farther away. Okay.
So I guess we do like these massive sky surveys. It's like looking for type 1a supernovae.
Exactly right.
And it's like, oh, there's one. And then it like figures out the brightness, and then we can measure the distance to that galaxy, and then finds another one. And we can measure the distance to that galaxy. We're looking for those supernova in the galaxies. They're pretty rare, but often enough that because there's so many galaxies, we can actually do it. It's kind of cool.
Absolutely, super cool. And the critical factor is that they always occur at the same physically predicted number. And so they call them standard candles because in the sky, they'll always be the same brightness. The only differing factor is their distance. Okay, so now that you know the distance to galaxies, then you can say, let's look at their spectrum. Let's look at their colors that they generate. And then you plot out the distance of a star, therefore the distance of its galaxy, and you see that the ones that are farther away are going even faster. And so therefore, it's a measurement. There are many steps along the way, but it's a measurement that the universe is expanding faster and faster as a function of time.
Yeah, so I guess it's a very, very, observationally based law. And exactly. I don't know, the theory and the detection of dark matter is not as well established. We're always pointing back to the measurement. It was definitely true because we measured the damn thing.
It's there.
So we got to explain it at some point and measure what is dark energy, so that why are we doing
figure
this?
Out so that we can understand how the universe works.
That's right. As we want to understand how the universe works.
And maybe one day we'll make a new product out of it. I don't know. There's This is some economics aspect of it. However, understanding how the universe works is already quite important because otherwise, how can you survive?
Yeah, I guess when people were first like trying to understand the planets and the moons and the solar system, there was no practical application. But through the process of learning that, there was all these offshoot things that needed to be developed so that human society could progress. But you couldn't have predicted what that was going to be beforehand. You just were curious.
Right. You're curious, you figure out how things work, and then once you know how things work, then you can devise products or solutions or I don't know, whatever.
Yeah, in fact, we look at like old civilizations and we're like, how advanced were they? Well, hard to find technology. But what was their understanding of astronomy? Let's look.
Incredible.
Right. Oh, they knew about eclipses and they knew how to predict the seasons and different. Oh, they're pretty advanced. But practically, probably not that much coming from it. We're like measuring their curiosity, meaning that's somehow related to their advancedness. Sure.
Yeah. Who knows? The discovery, or I guess not discovery, but the understanding of dark energy could be what allows us to do fast and light travel, for example. But up to now, like no idea how to do it.
Right. There could be some serious understanding that needs to be forged to understand it, which then leads to all kinds of offshoots that we didn't predict.
Mm-hmm. Cool.
Yeah.
The bad side about this is that if our universe is forever expanding, then there's only so much energy in the universe. And so if it gets spread out over a larger and larger and larger distance, the entropy goes to zero. All right. So the available entropy goes to zero, which means it's cold.
Yeah, we got a couple
whatever.
billion years to solve that one. So
Yeah, we get not a problem. Like whatever.
whatever. We'll just start sprouting new universes with new entropy. We'll be fine.
Yeah, maybe. Not our problem.
Nope.
See you next time.
All right. See you next time.